All right, class. So I'm going to go over here real quick, kind of how to set up for. All right, sorry about that. Let me come back to here. Here we go. All right, so what we're going to talk about today is your loads activity. And so let me quick. Okay, so your load activity is going to be the following. The idea here is anytime you're putting together a new building, you got to understand the design loads. And in this particular case, we're going to use an example of designing for a high school in the suburb of Chicago, Illinois. The enrollment here is about 2,500, so similar to Northville High School. And we're going to use this to select some appropriate joists, which are different beams based on the loads in that area. Okay, so here's a kind of floor plan view. We see some beams, girders. There's a couple different lengths here. So this one is 16 feet long, 20 feet. And then the overall span between the columns looks like it's about 21 feet. Okay, so we'll take a look here. And when you're submitting your assignment, please make sure you're showing your work. I need to see that in order to get credit. So again, I'll be going over some parts of it, but you still need to make sure you're writing things down and including some screenshots in your submission if you're going to get credit. Some of them you might be able to just type in as well. Okay, so here we go. Here's our procedure, calculating design loads. 1 second here. I'm going to pause my. All right, sorry about that, guys. There's I had a visitor there for a second. All right, so let's get back to it. So here's some of the criteria you need to think about while we're going into our design. So it's going to be a low slope roof, or sometimes referred to as a flat roof. It'll be steel roof deck. There'll be 5 inches of rigid insulation. We've got a built up roof, and it's going to be a double span. And so notice that it's going to be, the deck's going to be cut, so it's a continuous span from one beam over the top of a second, and it ends on a third support beam. Okay, so again, that's kind of what you'll see here in the roof plan, how it's going to cover over that gap. All right, let's see. We're dealing with the mineral fiberboard ceiling, and the roof is going to support mechanical, electrical, and plumbing. That's the MEP, and that's a total of 10 pounds per square feet. We're doing this in an urban environment around other buildings. All right, so question number 1. We want to calculate the snow load for a low slope flat roof, and we're going to use the following coefficients. So we're going to start off with a 1, that's the environment. So it's going to be urban, as mentioned before. The CT, this is going to be based on temperature, also a 1. And then we're going to assume it's a low slope roof. So that's why we have also a coefficient of 1 for that. Okay, so that makes our life a little easier. But still a few things we need to look up. First off, over here, we're looking for high school category. Okay, so where we get this value from? Did I realize? Oh, there we go. Okay, so high school category, I'm going to have to look this up in the International Building Code. I've got a link down here for you guys. I'm looking for table 1604.5. Let's go ahead and open that up. Actually, I think I had it up already. Just kidding. All right, so let's take a look here. I've got it here, 1604.5. Risk categories, and I'm going to read over this. What type of building are we dealing with? It's a high school with 2,500 people. So if I see here, probably fits under 3. So I see it's building containing secondary school, occupant load greater than 250. All right, so that's us right here, and we want to go under risk category 3. Okay, so that's what I would probably write down here. Okay, this is risk category 3. And sorry, what happened? Oh, it's not letting me type in here for some reason. Oh, no, it happened a bunch of times. Never mind. There it is. Okay, so I'll type in a 3 right there. Okay, maybe I'll open this up a little bit. All right, there we go. All right, so high school category 3. Next up, let's go ahead and look up that importance factor now. So that's linked also right there. I know it's going to be a lot of looking up things in tables. And so now importance factor, I'm seeing occupancy category 3. That gives me an importance factor of 1.1. Right? Just as a side note, if you looked here at the other risk categories, if it gets up to 4, we're looking more at hospitals, police stations, things that are designated for earthquake, hurricane, or emergency shelters, things like that. So that's one even has an importance factor slightly higher. Okay, let's go back to our, so importance factor, that's going to be a 1.1 in this case. All right, and let's keep things moving. We've got the Chicago snow load is what we need to look up next. So by location, that's the next over here. Check IBC table 1608.2. So I'm going to go back to the IBC. And it'll take a second here to load. I need to find Chicago. So 1608. And I'm going to try to find that map here. So see here, keep scrolling down. I miss it? Maybe I missed it. Let's see here. 1608.2. 1608.2. Oh, I did miss it. 1608.2. Oh, there it is. All right, so let's see if we can kind of zoom in here on Chicago. So I'm not sure if you guys are familiar with where Chicago is, but typically it's right here, right along the lakes, right? So that's falling in this category of 25. Okay, that's 25 pounds per square feet. So I can come back to my assignment and let's type in 25 PSF. Open that up a little bit. Okay, and then finally, we've got to do a little bit of math design snow load. So this is the equation that we went through in the lesson. So I've got 0.7 times CS. Remember, CS was 1 for what we were given as a roof slope. CE, that's your exposure factor, was also a 1. CT, that's your thermal factor, also a 1. Importance factor is what we found for the categories, 1.1. And then finally, PG, the ground snow load for Chicago, was 25. All right, so you'll multiply all that together. Again, make sure you show your work somewhere here. Maybe put a screenshot, or you can just type it in. Find what that value is. I will let you do that calculation. Once you find that number, to find the minimum snow load, this is where you go back to the slides. That's actually the next slide from here. And then if that number that you calculated, if it is greater than, less than 20, then you just do IS times PG. So whatever the snow load was, which actually in our case was 25, and then you'll multiply that by, where did I go? Okay, so you multiply that number times the importance factor. Okay, if the number was greater than 20, okay, so you put the numbers in, it's greater than 20, then we come over here, we take the importance factor times 20. Okay. Any questions on that? You'll please feel free to reach out to me and I can help you out. Okay, so that should cover it for question number 1. Moving on, question number 2, find the roof live loading required by the IBC for flat roofs. So live loading requirements, I'm going to look for 1607.1. So if I click on this one, I'm going to get rid of some of these other ones I'm not using anymore. All right. So we're looking for 1607.1. All right. So in this case, we're trying to figure out for a flat roof, what kind of load are we anticipating for that roof? So if we scroll down, see if we can find it here. Okay, we have roofs and ordinary flat pitched curved roofs that are not occupiable, no one's living on there, is 20. Okay, so then I'm gonna write down 20 PSF for roof live loading required by the IBC. So 20 PSF. Okay, let's keep things going. Number 3, estimate the dead load of the roofing system by estimating the weight of all the components. And there is a table that you'll find here. We're gonna look for steel roof deck, insulation, built-up roof, suspended ceiling. Again, the mechanical, energy and plumbing, mechanical, electrical, and plumbing. We already given that earlier, so that's 10 PSF. add all this together, that'll give us the total dead load. Okay, so if I look in this weight of materials table, I'll get you guys started. I'm going to scroll down here. This is my weight of materials. It is a scanned document, so it's a little bit blurry, but eventually you should be able to find what you need here. Okay, so let's start off with the first one was steel roof deck. And so if I zoom in a little bit, let's see if I can get a better view here. Okay, so I'm going in, I'm looking for steel roof deck. So under roofing materials, I see steel deck without roofing or insulation, and we're at 2.2 to 3.6, right? And personally, my go-to is I would lean towards conservative, so I pick that higher number, 3.6. In the future, if you actually know which kind of deck you're using, then you can go check that out. Okay, so if I come back to here, I've got, for example, the first one I looked up was 3.6. That's in PSF. All right, so then I keep doing that. The rigid insulation, I look for that one. Rigid insulation. I'm always a little bit blind when it comes to these things. Here we go. Insulation and waterproofing. Right, so we are looking for rigid insulation. It is 0.75, and we do need to multiply that by 5. This is typically per inch, right? So I would take this value, be 0.75 times 5 inches, and that would be whatever value that is. Okay, so I keep looking those up. Built up roof, find that in the table. Extended ceiling, look that up in the table. Add those together and round up to the nearest whole number. Okay, so you'll get a number for that. I'll let you do that. And then forward, determine the total design load of the system. The hint giving to you here is I'm going to add the minimum snow load from question 1. So whatever this number was here, I'm going to add that to question number 3, which is what I just found, the total dead load. Add those together, you get your total design load. So it'll be, the equation essentially is total load equals the dead load plus the live load. All right, so figure out what that number is. All right, and then the last 2 questions here. Questions 5 and 3, sorry. 5, 6, and 7. Here's where we got to do some analysis on the current. Okay, so our current roof design for question 4 is going to be a number we need to follow. So select a steel roof deck, double span. We're going to choose it from this chart. So let's go ahead and pull that up. And remember a couple of tips on this. Sorry, I don't know why everything's loading very slowly here today. Okay, we're using a double span. Remember that was given here, double span. And from the chart, we're going to figure out what kind of deck we're going to choose essentially. So I come back over here. Okay, I'm doing double span, and then whatever number I find over here that first covers it based on the total size, right? So sorry, I do need to look back at my picture. So we're covering a 7-foot span, as you can see there. So 7 feet and whatever value we found for question 4. I'll just give it to you. For me, I found for question 4 was 26 PSF. So hopefully that's what you got as well. So I'm gonna come over here, 7 feet, double span, and in order for me to cover, let's see here. Oh, sorry, I lied. The total design was 48. So in order for me to cover that 48, I need a metal deck 20. Okay, so it's going to be type 20. Type of deck is going to be 20 there. All right, finally, questions 6 and 7. I'll get you started and then hopefully you guys can take over. So the tributary width for interior and compared to exterior. And the picture I brought back down here again. If you need some help with that, again, look at the slide. You went or review the lesson video from before. Okay, so first off, interior beam tributary width. So the interior beam, that's going to be one of these that are along the inside. So I can see here that the width that needs to cover is from beam to beam is 7 feet. Okay, so that's going to be my tributary width, 7 feet. For the exterior, the one thing I didn't cover in the lesson actually was for the exterior beams. Okay, because it doesn't have to, imagine it this way, this beam right here only has to support the things on the inside. There's nothing on the outside to support. So it really only needs to do half the work per se. So typically the exterior beam is just half of that value. So I'm going to say 3.5 is going to be 3.5 feet. All right, finally, uniform beam loading for each of those. So that goes back to our equations from before. So you take the values from, let me show you guys in the slides. So if we come all the way down to the end here, right, we did tributary area, that's what we just figured out. Now for the beam loading, we take that width, multiply it by the floor loading in pounds per square feet. That's what we found in question 4, I believe it was. Down here. Sorry, 1 second. Okay. All right, so that's what we have to do. So it'd be 7 feet. And like I said from earlier, I found my value to be about 48, I believe it was. So if I take 48 times 7, that'll give me my value of about 336. Right, so again, show your work here. It's always going to be this equation right there, floor loading times tributary width. Okay. So that would be your value for beam loading, and then similarly for the exterior, 3.5 times that total load. Okay, show your work there. And then question number 7 is similar, but now we're going to do it for a column. Okay, so for a given interior column, we're looking at the total area around it. And so again, you see the total gap here is 21, and on this side we've got 18 and 20. So this one's going to be a little bit trickier, but try to break it down. So beam length between column 8 and 9. So between column 8 and 9, we see it's 16 feet. Right, so this part here would be 16. Beam length between 9 and 10, that's going to be 20. So we got 20 there. The interior beam now is going to be kind of how we decide. We have to look at this table, and then we'll decide what kind of beam we need in order to cover for those various gaps. All right, so let's take a look at this table. It's taking its time here. All right, so how we are going to read these out. So if you see here, these are your maximum yield strength. So that's kind of like what it can handle along that given beam. Okay, sorry about that, guys. So one more time, we're here. So right now, we're deciding what interior beam to use and what exterior beam to use. Okay, so the interior between 8 and 9 compared to between 9 and 10. So they're different lengths. Okay, so for this first one, 16 feet. Remember, for the interior beam loading, we had to find that number here, right? And again, the number I found for this part was 336. Okay, 336, that's pounds per feet. All right, so then the way I'm going to use this table is, remember, I'm covering 16 feet, and I need to be able to support this 336 pounds per feet for the interior beam. All right, so coming back over here, oops, where am I? Here it is. Okay, so then I'm looking at, I'm covering 16 feet, that's the span. And then I'm looking here for me to cover that 336. I'm going to use these top values here. So 336, the first number I see that's bigger than that is here, 380. I would need a joist 12K1. Okay, so that's the one I need. So that's what I would put in here for my interior beam, 12K1. All right. I do the same for the exterior, except this time I'm going to use whatever value I got from the exterior beam loading. And then the only difference between this side and this side is now the beams between 9 and 10 are 20 feet long. So when I go to my table, instead of looking at 16 here, I'm going to look at 20, come across, see where I can find. I guess I can do this first one. Remember, we're doing 336. So now 20 feet, 336. The first one I see that is big enough, looks like is there's a 409 here. That might be my best bet. Yeah, so 409, that probably is what we want to look at. So I'll do 409, that's 12K5. All right, so hopefully you can do the same for the exterior beams. Remember, using the exterior beam loading at that given length, you should get a slightly different beam. Typically, those are going to be smaller, so you have smaller values in the exterior, higher numbers for the interior. All right. Now that long, video is fairly long, but hopefully that gets you what you need for this assignment. Answer those conclusion questions, thinking about why we treat different loads separately, how do they affect the structure, think about why you design the way we do combination designing, consider any load combinations, right? Why do we just look at a bunch of them? And generally thinking about how do the specs change if you increase the distance between beams. All right, I think that covers it, guys. So as always, if you need help with something, you obviously can ask me in person or send me an email. I can help you out. All right, good luck.